Applications of an equilibrium constant. What can K, or our equilibrium constant, tell us about a particular system? Can K tell us how fast a reaction goes? No, that deals with chemical kinetics. But when we talk about K, it does tell us how far the reaction will proceed to the right before equilibrium is established. A large K means that there's lots of products at equilibrium. A small value for K tells us that we have mostly reactants at equilibrium. So now we're going to deal with what's called a reaction quotient, or our Q value. And we calculate Q the same way that we calculate K. It's the concentration of the products over the concentration of the reactants raised to the power of the coefficient in the balanced equation. And it predicts the direction in which a reaction will go to reach equilibrium. If Q is equal to K, that tells us that the system is at equilibrium. But when we calculate Q, if it does not equal K, then our system is not at equilibrium, and it's either going to shift towards the product side or the reactant side in order to establish equilibrium. So if Q is greater than K, that means that there's too much product present in that system. The system is going to have to use up product and produce reactant to establish equilibrium. So the system would shift towards the left in order to reach equilibrium. If Q is less than K, that means that we're too far on the reactant side. There's too much reactant present. So we're going to have to decrease reactant and increase product in order to get Q to equal K and establish equilibrium. So the system would have to shift to the right to reach equilibrium. So here's an example. Let's say that we're told that for the synthesis of ammonia from its elements at 500 degrees Celsius, K equals 0.06. We're given a set of concentrations and we're asked to predict the direction in which the system will shift to reach equilibrium. So what we're going to need to do is write and balance our equation, write our K expression, which is the same as our Q expression, plug in the concentrations that we're given, compare it to K, determine whether the system is at equilibrium or not, and if it's not at equilibrium, which way is the system going to shift to establish equilibrium. So we'll write our reaction first. We're going to have nitrogen plus hydrogen to produce ammonia, and then the reverse reaction is going to take place, and we need to have a balanced equation. So we'll need to put a 3 here and a 2 here to get our balanced equation. Now we want to write our expression. And since we're dealing with concentrations and we don't know whether they're at equilibrium, we'll use the value Q. And it's going to be the concentration of ammonia squared over the concentration of nitrogen times the concentration of hydrogen cubed. The next step will be to plug in our numbers. So we've got 0 for our concentration of ammonia, 1.0 times 10 to the minus 5 for nitrogen, and 2.0 times 10 to the minus 3, which we're going to cube, for hydrogen. And that's going to give us a Q value of 0. So K is greater than Q. In order to get to equilibrium, we're going to need to get Q to equal K, which means we want to increase Q. To increase Q, we want to increase product and decrease reactant. So our system is going to have to shift to the right to establish equilibrium. And actually that makes sense because when we look at these particular numbers, we don't have any product yet. There's no way that the system could shift towards the left because we don't have any product initially. All right, so let's look at another example. We're going to use the same reaction, the same K value since that's a constant, but we're going to have different values this time. We want to calculate Q, predict the way that our system is going to have to shift to establish equilibrium. So we've got our equation, nitrogen plus hydrogen gives us ammonia. Oop, that should be a 3. We've got our Q expression. So the concentration of ammonia squared over the concentration of nitrogen times the concentration of hydrogen cubed. And now we'll plug in our numbers. So this time we've got 2.0 times 10 to the minus 4 squared over 1.5 times 10 to the minus 5 times 3.54 times 10 to the minus 1 cubed. And this time we're going to get 0.06. So our K equals our Q value, which means we're at equilibrium for this particular set of concentrations. Now let's do one more. Same reaction, same K value, different concentrations. So we've got nitrogen plus hydrogen. I'm going to put that arrow in 2 directions, which represents a reversible reaction to produce ammonia. We're going to write our K expression, nitrogen squared or ammonia squared over nitrogen times hydrogen to the 3rd. And now we'll plug in our new values. So we've got 1.0 times 10 to the minus 3, and we'll square it for ammonia. We've got 1.0 times 10 to the minus 5 for nitrogen, and 2.0 times 10 to the minus 3, which will cube for hydrogen. And that's going to give us, with 2 digits, 1.3 times 10 to the 7. That's a huge number. That means that K is much smaller than Q. We're not at equilibrium. We want to decrease Q to get to equilibrium, which means we want to decrease product and increase reactant. So our system is going to have to shift towards the reactant side or towards the left to establish equilibrium.